Ever wonder about the theory of general relativity and how it works? This question leads us to some of the most intriguing theories in all of physics, the theories of relativity. Penned by the remarkable physicist Albert Einstein, these theories have shaped our understanding of the universe. Let's start at the beginning, with special relativity, which Einstein introduced to the world in 1905. This theory explains how speed affects mass, time, and space, and it introduced the concept that the speed of light defines the relationship between energy and matter. It was a revolutionary idea, challenging the existing laws of motion established by Isaac Newton. Fast forward 10 years to 1915, Einstein expanded his theory with general relativity. He acknowledged the existence of gravity, explaining how massive objects warp the fabric of space-time, creating a distortion we perceive as gravity. This theory describes gravity not as a force, but as a result of the curved space-time, another groundbreaking concept. Hold tight as we dive into the exciting world of Einstein's relativity theories. Before we delve into general relativity, let's understand its predecessor, the theory of special relativity. At its core, special relativity is all about perspective. It's like watching a lightning storm from a moving train versus watching it from a stationary spot. Your viewpoint changes your perception of the event. This theory, crafted by Albert Einstein in 1905, was a game-changer because it proposed that the laws of physics are the same for everyone, regardless of their motion or location. Now, how does speed affect mass, time, and space? Well, special relativity introduced the idea that the speed of light sets the bar for the relationship between energy and matter. This might sound a bit abstract, but it's actually incredibly impactful. It means that a tiny amount of mass has a huge amount of energy locked inside it, just waiting to be released. This concept is captured in the famous equation E equals mc squared. But what about time? Here's where things get really interesting. Special relativity predicts that time doesn't tick the same for everyone. If you're moving, time actually slows down for you compared to someone who is stationary. This is known as time dilation. It's been observed in real-world experiments, like those involving astronauts and GPS devices. It's like time travel, but in slow motion. And then there's the concept of simultaneity, which tells us that things happening at the same time for one person might not be simultaneous for another person moving at a different speed. That's right, even the idea of now can change depending on how fast you're going. So that's special relativity in a nutshell, but what about general relativity? Now imagine taking special relativity and adding gravity into the mix. That's where general relativity comes into play. You see, Albert Einstein, the mastermind behind these theories, expanded on his own theory of special relativity by acknowledging the existence of gravity and explaining how it interacts with space-time. In the realm of special relativity, we dealt with high energies, fast speeds, astronomical distances, but there was no room for gravity. Einstein, however, knew that gravity was a fundamental part of our universe and couldn't be ignored. So he took the concept of special relativity and added a new dimension, gravity. He proposed that massive objects like planets and stars warp the very fabric of space-time. This warping, this distortion, is what we perceive as gravity. It's like a bowling ball sitting on a trampoline. The ball sinks into the fabric, creating a dip around it. Now, if you were to roll a marble near the bowl, it would spiral towards the heavier object. That's a simple way to visualize how gravity works in general relativity. But how does gravity affect space-time, you ask? Let's find out. At the heart of general relativity lies a fascinating concept: gravity as a result of curved space-time. This idea might seem a little abstract, but let's break it down. Think of space-time as a giant invisible fabric that stretches out in all directions. When a massive object like a planet or a star is present, it warps or distorts this fabric, creating a kind of indentation. Now picture a smaller object such as an asteroid coming near this indentation. Instead of moving in a straight line, it follows the curve of the indentation. To us, this movement appears as if the smaller object is being attracted by the larger one. We perceive this as gravity. But here's the twist. It's not just the presence of a massive object that causes this warping. The object's speed and direction of motion can also affect the curvature of space-time. This is why the planets in our solar system orbit the sun in elliptical paths, not perfect circles. Now you might be wondering, how do we know all this? Since Einstein first published his theory in 1915, it has been confirmed by a multitude of observations and experiments. For instance, the shifting orbit of Mercury, the distortion of space-time by spinning objects, and the stretching of electromagnetic radiation in a gravitational field have all provided evidence supporting general relativity. Furthermore, in 2016, we detected gravitational waves for the first time. These are ripples in the fabric of space-time caused by cataclysmic events, like the collision of two black holes. The detection of these waves was a monumental moment in physics, and a striking confirmation of Einstein's century-old theory, so we've seen how gravity isn't just a force, but a distortion in the fabric of space-time itself. And there we have it, a whirlwind tour of Einstein's theories of special and general relativity. In these few moments together, we've journeyed through some of the most profound concepts that have shaped our understanding of the universe. Let's take a quick look back. We began with special relativity, Einstein's groundbreaking theory that introduced us to the idea that speed affects mass, time, and space. It was a game-changer, challenging the then-prevailing Newtonian physics and setting the stage for Einstein's later work. Special relativity showed us that time and space aren't absolute, but are relative to the observer. It also gave us the famous equation E equals mach squared, revealing the deep connection between energy and mass. Then we transitioned to general relativity, Einstein's magnificent theory that expanded upon special relativity by incorporating gravity. Instead of viewing gravity as a force, as Newton did, Einstein saw it as a warping of space-time. Massive objects distort the fabric of space-time, creating what we perceive as gravity. The differences between the two theories are significant, yet they are two sides of the same coin, both integral to our understanding of the universe. While special relativity deals with high energies, fast speeds, and astronomical distances without gravity, general relativity takes into account the influence of gravity and massive objects. These theories, though complex, have practical applications in our daily lives. From GPS technology to understanding the behavior of celestial bodies, they continue to shape our world. But now it's your turn. What aspects of relativity theories do you find most intriguing? Is it the concept of time dilation, the relationship between energy and mass, or the idea of gravity as a distortion of space-time, or perhaps it's something else entirely? Share your thoughts in the comments below.